All right, good. Okay, so before we get started, again, a reminder, next week we'll be in person, right? So hopefully starting from next week, we'll be in person. The university has warned us that there may be sort of significant number of students isolating. We'll see. So if that happens, we'll make an adjustment. We'll make an adjustment if that happens. But at least for now, the plan is to next week will be in person. And at least by looking at the room, technology in the room, there is not an easy way to record the lecture. Right? So if there's just a very old building, it's in the arts building, it's not, there's not much we can do there. Right? So if the need for recording arises, I'll try to figure out a way to record lectures. But for now, at least, for the next few weeks, plan to be in class or in person. I know 8:30 is a very early class. I did not know this class existed before this quarter, but try to do the best you can. Show up on time. Okay. Question about that? Question about sort of in person versus remote, different protocols. Okay, all right. So then let's continue from last time. So last week, last class, we start talking about sort of wind power or wind energy. Right. So next, what we really want to do is we want to link the energy or power in the wind to the amount of power you can extract from the turbine. Okay, so we have some wind power. Again, that's coming into a turbine. Basically, our goal is to get to a point. So you won't extract all the power that's entering the turbine. Okay, we're far away from extracting 100% of the power. So what happened is there'll be some constant, or not constant, some coefficient of performance times the amount of wind power that comes into the turbine. Right? So think of this coefficient of performance as something that's between, say, 0 to 1. Right? So there's a fraction, we get a fraction of the power that comes in. So the goal of this class and possibly sort of early next class is to figure out how do you control this number. Okay, so what we want is a big coefficient performance. We want this number to be as big as possible. We want to extract as much power out of wind as possible. So how do we do this? Okay, how do we, the goal is to say, how do we get as much power as possible? What do we control, right? If we have a turbine, what do we do with the turbine to extract this, to make this number large? Okay, so that's our goal, right? So our goal is to get to this point to write down an equation for CP. Okay, so it turns out, again, we won't even most times get to 50% of the power, but still there's a range of power we can extract. I want to see how we can extract this one. Okay, so we can sort of extract power. So we want a big CP most of the time, but also sometimes we want a small coefficient performance. Right? When we don't want to generate power, we want to reduce the coefficient performance. So let's see how that can be done as well. Okay, so that's where we're trying to get to. So a little bit of review, right? From last time, we looked at the kinetic energy in wind. This is basically this is the formula we always have, half mv squared. We're always looking at a cross-sectional area A, right? We're always so the turbines, the blades trace out a circular area of area A. So within this area, the amount of mass you can move through this area in a certain amount of time is given by the area multiply the density, right? How much stuff you have, multiplied by the density, multiplied by time, multiplied by speed. This is the amount of mass in a certain amount of time we have moving through an area. So you put all this together, we have kinetic energy as half A times the area times density times time times V cubed. So the big thing is this is a cube. This is a cubic relationship. Okay, so cubic relationship basically says that you a little bit increasing speed buys you a lot of half. Okay, buys you a lot more energy. So when speed is a small increase in speed, this can lead to a large increase in energy. Okay, so just because it's a cube, right? This is a cubic relationship. So a lot of wind turbine placement, where you place a turbine, is basically, can you extract this increasing speed? Okay, you want to place a turbine where the speed is high. Right? So a doubling in speed is 8 times the energy. Right? So any ideas of how, like, so where would speed be high? If you're placing a turbine, where do you think we should put the turbine? Where will we have high speed?
You could put it somewhere where the wind funnels into a valley or something.
So that typically is not where we would put it, because then you're constrained by size. Right. So you can put it between 2 buildings, but then you're very constrained by size. Right. So let me rephrase the question: where can you put many large turbines where the speed is high? Let's say you want a farm of them. Where do we want to place them?
Offshore, for example.
Right. So one thing that impacts wind speed is whether the surface is flat or not. Okay, what you really want to do is you want the Earth to be very flat where you put your turbine. So actually you want sort of flat surface. Okay, you want this, you don't want anything sort of, before the turbine. You don't want a building, you don't want a mountain. So you want to, for example, water. Okay, so that's why offshore is very good. It's very flat, there's no obstruction for air to flow. So you want a very flat surface where you put it. What else? So why mountain? Why mountain? So you put it at the coast because it's the surface is flat. Why mountain?
The high altitude.
Right, height, right? So there are 2 main impacts to wind speed. Is whether there's something before, right? Whether you have the surface, the flatness of surface, and the height. Okay, the higher it is, the faster the wind speed. Okay, so this comes from that the friction is much lower. Okay, so you want to put it where it's flat, and you really want to build a turbine that's really tall. Right, so you have higher elevation, you have higher speed, you want so the best place to put it is put a really big turbine offshore. Right, so that's sort of the best of both worlds. If you can't, then you go for sort of higher ground, where you try to maximize the speed. Okay, really, the goal is to maximize speed. So you want sort of, so everything for wind turbine design, sort of the #1 factor is you want to increase in speed. Or you want to optimize for speed, actually. So you want to max wind speed. Right, just has such a, so the energy has such big dependence on speed. So this is a factor. So it almost always makes sense to increase this as much as possible. Okay. So it's always in your back of your mind. Remember, this is sort of the #1 factor. So if you look at the formula, So A depends on the size of your turbine. So on the build big, right? V is given by the speed of wind. So one thing that in this equation that's sort of a little bit also depend on nature and where you put the turbine is this delta, this density. Okay, then there's many formulas for density. So there's a chatting question. So why is friction higher at lower elevation? It's just a drag on Earth. So if you think of air as a fluid, right? Think of air as a fluid. It's actually it's sort of there's a lot of drag when the air goes through a surface, and that drag will slow air down. Okay, so it's a fluid that has drag. Does that answer your question? Yeah, so you want to sort of get away from the surface of the Earth to have higher speed, right? So one trade-off as you go higher is that air becomes less dense. Okay, so there's a slight trade-off between speed and density, right? So there's air density in this class. We'll have a couple of different equations to measure air density. Air density depends on the elevation, how high you are. Also depend on the temperature. Right? It depends on two things. And this is, for example, one sort of empirical equation that how air density depends on this kind of things. Okay. So we're not going to derive this equation. It's just as long as you know there is an equation to look at, then it's fine. Okay. You don't need to sort of memorize this equation, anything like that. Right? So there's just it's good to keep back in your mind as if you go very high, then air may become actually less dense. Right? So you go high, but not, for example, if you put a wind turbine, let's say a kilometer above the ground, there are designs like that. You put on the airship, you put it very high above ground, have very high speed, but then you have some trade-off on air density. Okay, so there's trade-off on density. So this is another equation for air density. If you know the pressure, if you know the temperature, then you can also compute the density. So depending on different situations, it may be easier to measure pressure versus height. So we'll use the second equation. Okay, but really these are just equations you can look up. There's not much going into it, right? So often we don't bother computing with these equations. Okay, so in a lot of terms, actually in wind engineering, we don't bother with this equation. We sort of have a default value for density of air. Anybody know what that is? What is a nice round number for density of air? Anyone know the default number? When you think of how, like say you have a cubic meter of air, how much does it weigh? What's the mass of that? So the default number, we very often will use as we assume the density of air is 1 kilogram per meter cubed. It's not exactly this number. It's actually, if you look at sea level at room temperature, is about 1.2. But that, being this wind engineering, we like a round number. If you assume it's 1 kilogram per meter cubed, you're not off by that much. Okay, so we often, if you see a problem that doesn't give you the density, but also doesn't give you this sort of parameters to compute the density, the assumption is almost always air is 1 kilogram per meter cubed. Okay, it's just and in a lot of software, you actually don't bother computing, or in a lot of papers, just sort of assume this is not. Okay, so a nice round number we have. It's not exactly right, but it's good enough for a lot of our purposes. Okay. Right, so this is the assumption we make. So next is we compute the energy, right? If you look at this equation, there's a weird variable t, time, that's here. Right? So we don't really want to talk about wind energy because that depends on time. So for now, we want to talk about wind power. Okay, we want to convert from energy to power. going to talk about wind power. So when we talk about wind power, what we have is, so we want to talk about, right? So there's two dependents. This is the size of the blade, basically. If you have a larger blade, you have more energy. This is time. So often the metric we are interested in is this power density rho, right, in watt per meter squared. And so at this specific location, how much power do I have? Then we can design how big is a blade and how, if we run it for a certain time t, this is energy we extract. Okay, so we want to talk about power or power density. So it's very easy to convert energy to power, right? So power, what we have is P. Okay, so one thing that's, let me write this and I'll explain a notation difference. A delta, okay. So if you look at this variable, this is W. This is often also used for wind speed. We also often use V for wind speed, and these are used interchangeably in a lot of contexts. So also, if you look at the reference book, these are used interchangeably. So unfortunately, a lot of equations you see either W or V being used. So W for wind, right? So speed of wind. So just keep in mind that W is also just speed, is meters per second. Okay, so this W is measured in meter per second. It's just a speed. But in a lot of equations, you see it written as W. In other equations, you see it written as V. So there's an unfortunate notation mix up. Okay. So to follow sort of the reference book a little bit, we'll use W in this kind of equations. So in case you're reading the book, we can compare. But it's just standing for V, just standing for speed. Okay. So power, we get 1/2 A delta W cubed, speed cubed. And then the density is just power divided by area. Okay. So this is 1/2 delta speed W cubed, speed cubed. Okay. So this gives us a unit of then watt per meter squared. Okay. So this is, if you build a 1 meter squared, if your turbine traces out area, that's 1 meter squared, you get a power of rho, right? So this is air power density. Okay. So again, the thing to note is the scales, again, with the cube of the speed. So power density, so the energy, the power density, all scale with cube of speed. Any questions about this calculation? Does this mean assuming wind speed relative constant? Can you explain that question up there? So constant.
Yeah, wouldn't there be like the power is derivative of energy, right? So wouldn't there be another term? Just wondering if that ever comes up.
Right, yeah, so that's a good question. Sorry, so the question is, even if you fix a location, the speed is not always constant, right? It's not a constant speed. How do we think about that? So for now, assume the speed is a constant, at least for a relatively short amount of time. When we go into the probability section of the class, we'll look at how do you deal with the fact that the speed is not constant. Okay, the speed can take on many values. How do we think about power? Okay, and this cube again comes in there actually. Okay, so the average of the power is not the average speed cubed. So that's one thing we'll sort of drill down when we get to probability. For now, think of we're operating this at a relatively short amount of time. We have constant speed, and that's the power density we get at this particular speed. Any other questions? Okay, all right. So when you do homework questions or exam questions, you may be asked to compute the energy, the power density. So the good way is to look at the question and think about the units. Right? So often the mistake is you multiply by the area, you forgot to multiply by the area, or you multiply the area where you shouldn't have. So when you do the question, read the question and think about the units, right? If asking for density, then you should divide out the area. If asking for power, then you should multiply density by the area. Okay? Just to read the question and think of the unit you should have. That's the answer. Okay. So again, that's just a plot of something cubed, right? We want to emphasize that this scale goes up really, really, really fast. Okay, so doubling, right? So you think about this, right? So you have energy in 1 hour of, let's say, 20 mph wind. This is equal to the amount of energy in 8 hours of 10 mph wind. Okay, so higher speed, right? So higher speed means you have to extract a lot of power, a lot more energy. So if you again think about a case where the wind speed may not necessarily be constant, then you go for places where the top speed is high. Okay, right. So this cubic relation really buys you a lot. So a relatively short period of high speed is worth a lot compared to a long sustained period of lower speed. Okay, so you may see turbines put at places. Sometimes it's very calm, but then sometimes very windy. And often it makes sense to go for the place that's sometimes very windy and not often all that steady. Okay, so again, it comes from this cubicle. It's very nonlinear. So really a little bit increasing speed by so long. Okay. So this cubic relationship also gives us an idea of why wind power prediction is difficult. Okay, this also gives us that, right? So you may think, well, why can't we predict wind within 20% accuracy or 25% accuracy? Why they're so hard, right? You have all those weather models, you have supercomputers, you have all those kind of things. Okay, so let's see why it's hard to do prediction for wind speed, for wind power. Okay, so suppose we can predict wind speed as, this is, you have 8, let's say your wind speed is the following. Okay, so we say at the location, the wind speed is about, between 8 meters per second to 10 meters per second with a mean of 9 meters per second. Okay, so this is not a bad prediction, right? Where, 1 out of 10, about 10% error. This is not so bad. So we'll predict this as so the error in speed prediction is around 10%. Then what is the error in the power prediction? Right, let's say you got speed pretty close, right? 9 compared to 8 compared to 10 is not so different. You walking may not feel the difference. Okay, so now let's see power. Let's look at power. So power, so 8 cubed, right? So we're cubing the speed. This is 512. 9 cubed is 729. 10 cubed is 1,000. Okay. So if you get speed within 10%, look at the power difference. Okay, so this is a very large gap. Okay, this is a very large gap, right? This gap comes from the fact that you're again cubing the speed. Okay, once you start cubing something, even if you can predict speed well, power is not predictable. So the error in power prediction is often much larger than the error in speed prediction. Okay, so it's not that we can predict speed. It's that even if you get speed, power, because you're cubing the air, just magnifies. Okay, so and when you operate the grid, you really don't care what the speed prediction is, right? If I'm operating the grid, I want to know how much power will that wind turbine deliver. Right? I don't care how close you get to the speed of your turbine. And then even getting to 20% deadhead is not easy. Okay, so yeah, right. So this is why a lot of people sort of think, oh, wind power prediction we can do, because look at all the weather model, right? I can, predict wind speed within 5% error. But once you start cubing things, especially when you're cubing large numbers, that error gets dramatically amplified. Okay. Any questions about this? Right. So this is why if you work in this industry, they'll always tell you, right, wind speed is not wind power. Wind power is a much more complicated thing than speed. And again, even today, predicting wind power, we're not very good at. We're not very good at predicting wind power. Okay. All right. So there's inherent error. There's just inherent error. That's here. Okay. So this is again, this just drills down to the cubic relationship, where whenever you look at speed, think to power, think that's something cubed. Then the last part of the equation, where we have right? So we have a factor of A. This is something we can design, right? So we get to design the area A by how large a blade we build, right? Whereas the wind speed is really given by nature. Right? You pick a site, and the wind speed is whatever the wind speed is. Whereas the area of the area you sweep out is determined by the size of the turbine you build. Okay, and if you look at the area, since we trace out the circle, this is pi r squared. Right, so it's a square of the size of the blade. The longer the blade, you have a squaring effect in the area. Okay, so that's why you want to build big turbines. Okay, you pick a site with highest wind speed, and you build the largest turbine you possibly can at that site. Because the power is proportional to area, and area is the square of the length of the blade. Okay, so you also want that to be long. Questions about these? Okay, right. So all this kind of factor, right? So a lot of trade-offs are not linear. Okay, so when you design this kind of things, so we're very good at thinking about linear trade-off, right? You lose 10% here, you gain 10% there. All these designs, the trade-off are not linear. So you have cubes, you have squares, so it makes the trade-off calculation a little bit more complicated. Right, so let's do an example. Let's say we want to compute the amount of wind energy you capture in a 1 meter square area under the following conditions. Okay, so we have 5 hours of constant wind speed. And we want to look at for different speeds, what is the difference in the amount of power we can capture? Different amount of energy we can capture here. Okay. So the equation again is very simple equation of A delta T speed cubed, right? And then we know A is 1 meter squared. Delta is 1 kilogram per meter cubed. So these are given in the problem. Right, we have a meter square area. The density is 1 kilogram per meter cubed. So let's see how much energy we can capture. So let's say for 4 meters per second, we have the kinetic energy is half 1 times 5 hours times 4 cubed. kilowatt hour. Okay. So again, we want to state things in terms of kilowatt hour. Right? You want to pick the most, you want to pick the unit that makes sense. Okay. So you can state this as 16, for example. Actually, yeah. So for most of the calculations, you should state in the unit that's most convenient for people to read. Okay, for this kind of numbers, it's easier to state in terms of kilowatt hours. So 5 meters per second, so 8 meters per second. Same equation, right? We're just cubing 8 instead of 4. You get 1.28 kilowatt hour, 9 meters per second. Kinetic energy is 1.82 kilowatt hour. Okay, right. Right, so this again is trying to show that going from 8 to 9 makes a big difference. Going from 4 to 8 makes a big difference. Going from 8 to 9 still makes a big difference. Okay, so the margin of return for increasing speed is very, very high. Okay, so this is during homework. State energy in kilowatt hour or megawatt hour. Okay, so these are the units that we see in practice. These are the units that make sense. Okay, so do not state your solution, your energy in terms of joules, right? And also do not state in watt hours. Okay, stay in this sort of more common units we see in power engineering. Okay, so those are technically correct, right? You could state 1.82 kilowatt hours in joules. I have no idea what that is. And, right, if I have a fairly good idea of how much energy is in 1.82 kilowatt hour, if you convert this to joules, I have no idea what that is. Okay, so you want to give units that make sense. Right? In our field, these are kilowatt hours and megawatt hours. Okay. Right, so if you do this in your homework, the first time we see it, you get a warning. You keep doing it, then we'll start deducting points from your homework. Okay, so again, you want to communicate to people in the right units. Any questions for this example? Okay, so the equations are simple. It's just knowing where to find them. Okay, just knowing where to find them. Okay. All right, so the last thing is we want to look at so often when you compute wind speed, it's actually hard to measure the wind speed at where you, right? It's also actually hard to measure the wind speed at where the turbine is. So give you an example is, if this is ground, right? If this is ground, your turbine is not close to ground. Your turbine is probably somewhere high up here. Okay, the turbine is somewhere up here. So this is where your wind turbine is. That's where ground is. You may not always be able to measure. You may not always be able to measure at exactly the right height you want. Right? If your turbine is 120 meters, you may not always be able to just put a sensor directly at 120 meters right there to measure what the speed is. So it's useful to have a equation that tells you if you measure the speed at the H0 at some nominal height, if you now change the height of your turbine, how will the speed change? Okay, so this comes out if we measure H0, I want to compute the speed at H. Okay, so I have elevation H0, that's something convenient for you to measure. And then you want to change different height, and you want to compute the speed without remeasuring. Okay, so measuring wind speed at high elevation is not trivial. Okay, so you want to do all these kind of things. And this relationship is basically given by this sort of scaling factor. Okay, you have this, so if you want to rearrange this, you can think of the speed as a fraction of some factor times the nominal speed. And this is given by the ratio in height. Okay? This is just given by ratio in height. Okay? So alpha is a parameter. Alpha is some empirical parameter that we fit. Okay, so alpha, there's different values for alpha. If we have open land, alpha is about 0.143. With water, 0.1. Okay. So what this does is if you have, let's say, flat land or water, then the height is doesn't matter all that much. There's some dependence on it, but the dependence is typically weak. It's fairly weak dependence. If you look at city, alpha, this is much larger dependence. This is around 0.4. So in your city, going up higher really makes a difference. If you're in open water, the dependence on height is not terribly large. Okay. All right, so this is just an empirical formula. Right, so if you ever do a homework question on this, we will tell you what alpha is, right? So you don't need to remember any of these values. But this is just keep in mind in practice, we're not going to measure at every elevation. Because we measure at some elevations, then we use equations like these to figure out wind speed at all kinds of different elevations. Okay. All right, so again, since power depends on the cube of the speed, right? Power is a cube. So this is the power depends on a factor of 3 alpha. Okay. Speed is a factor of alpha, and power is a factor of you raising to 3 alpha. All right. So let's do an example. Let's say we measured at 100 meters. The wind power density is 2.5 kilowatt per meter squared, and the wind speed is 10 meters per second. Now we want to say, what if we put, if we look at 50 meters, what is the wind power density? Okay, so we measured 100, but now we want to compute at 50. Okay, so here for open terrain, open land, alpha is 0.143. All right, so this kind of questions are very simple to do, because if you look at all the equations, the ratio of power is equal to h over h naught to the power of 3 alpha. And then the power density, right? Power density follows the exact same relationship. Right? The power density follows the same relationship. It's also changed by a factor of 3 alpha. So the power over power, the ratio of power is the same as ratio of power densities, because the areas divide out. So this is h over h naught to 3 alpha. The density is what you measure at your nominal height, adjusted by a factor of h over h naught 3 alpha. So this is 2.5 kilowatt per meter squared at 100 meters. We're looking at 50 meters over 100, right? This is the ratio of the elevations. Then this is 3 times alpha, 3 times 143. And compute this, you get about 1.86 meter squared. Okay. So this is a typical calculation you do in the field. Okay. So you measure at either 550 or at 100, then you can look at the speed at different elevations. Any questions for this? Okay, so right. Okay, so so one assumption that we made through here one assumption we made is if you think about the wind turbine, what wind turbine traces out as a circle, and we sort of assumed that the speed through this circle is constant. Okay, we assume sort of constant speed through the circle. That's why we get A multiplied by the cube of the speed for power relationship. But because wind turbine, there's some elevation change, right? Wind turbines are large, there's elevation change. So the top of the turbine is at a higher elevation than the bottom of the turbine. And by these equations, there should be a difference in speed. Okay? So in most of our formulas, we will not take this into account. But in the first homework, which will come out probably late today or early tomorrow, the question that if 551 students has to do is to figure out a more accurate equation, taking into account the wind speed difference at the top and the bottom. Okay, so you see this equation, you'll see this question. All right, so this basically just integral. You just have to integrate. You have to integrate something cute. That's sort of all you have to do, right? But that's the type of question you'll see in the homework. That's sort of optional for the 451 student. For a 551 student, you should be able to do this integral. Okay. All right, so this is the assumption we make. Right? You may often wonder, hey, I have top and bottom. Why we're sort of treating the speed through the circle to be constant, whereas in reality, that's actually not the speed is not constant through the circle. Okay, so there's an adjustment factor. It just we typically don't deal with that factor in the equations we have in the course. Okay, so something to keep in mind. Any other questions? Okay, all right. So next we'll look at turbine design, but actually this gives us a natural point to break in the class. So let's break for 10 minutes. We'll come back at 9:25. Then we'll look at turbine design. So up until now, all we talk about is how much is the intrinsic power in wind. The turbine design will tell us how do you get that power to the turbine, right? How will the turbine extract that power? Okay, so we'll pause for 10 minutes. Then we'll come back at 9:25 and look at turbines. All right, let's get started again. So to extract power from wind, right, from the moving mass of air, we'll do this by turning turbines. So this turning turbines is exactly how you fly airplane. Actually, this is not very different to how you would fly airplane. Right? It's just an airplane moves through the air, right? Airplane lifts up, whereas a turbine just turns around the axis. Okay, so if you look at the turbine, if you look at this turbine, then all it does is wind will come into this sort of airfoil ship. Well, they will hit this airfoil, and then you try to generate lift. Okay, so wind hits airfoil generates lift, right? So when you fly airplane, as you are providing thrust, right, through the engines, but that's exactly the same as wind is hitting you. So in this case, it's wind hitting you. So you have a high-speed moving air mass hitting you, and then you provide lift. The blades cannot really lift up, so what they do is they turn. That's all we have. The basic operating principle is very simple. Right? So what we really care about is, right, so how do you control the amount of lift you generate? Okay, at the end of the day, we design the blade as, okay, I know I will have some lift, but what really controls the amount of lift I generate? By controlling the amount of lift, this controls the amount of power I get. So again, we're thinking of wind turbine as airfoil, right? As airfoil. So you have something that's hitting this edge. Right? You have a moving. So you have wind, you have air hitting the leading edge of the airfoil. Okay, so you have a leading edge. This is where the wind hits. You have a trailing edge. And we have, right, so there is a chord line. So this is so-called a chord line. And we have some center of gravity. We have sort of, okay, this is center of gravity. So the airfoil shape is a little bit funny shape. So it's not an easy shape to describe. So have a leading edge, have a trailing edge. What the core line does is we often want to measure some angle called the angle of attack or pitch angle. Right? You think of a blade. You want to say, okay, how much is the angle relative to wind? Okay, but because this shape is this little bit funny shape, well, when we measure the angle, we need to pick a line to measure the angle from. It's sort of this curvature shape. So the core line is something we use to measure angles with respect to. Okay, so think of this core line as you measure angle with respect to this core line. The center of gravity is the center of gravity of the airfoil. Right? So when we think about the lift, we can think of a lift being, we can think of this airfoil as a point. And when you have a lift, you're trying to generate a lift force like this. Okay? This is our goal of looking at airfoil. Okay, so the shape is complicated. We will not really go very deep into the shape design. So if you do aerodynamics, then there are people's whole jobs as to design the airfoil shape. A lot of design in the wind turbine goes to exactly how to design the shape. Okay, for us, we won't look at it. So for us, we'll think of the airfoil as very simple. It has two edges. We have a core line. This is really for us to measure angle. Okay, so the core line is really for us to talk easily about angle measurement, right? Have a pitch angle of 15 degrees. What exactly is it measured relative to on the airfoil as to this line? And we'll have a center of gravity. Right, so we will think the airfoil turns will actually most of the equation will be the center of gravity turn. Okay, really, so we won't really go into the shape design of this thing. Okay? So if you want, this was just a better drawing, just a better drawing of the figure we have. Okay. Right. So now comes to the fun part, right? Why does right? So why does this? How's lift generated? Right. So this is why does airplanes fly? For wind turbines, this is how is lift generated. Okay. So I'm sure you have all heard of this theory. We have longer upper. You have a longer upper camber, right? So you have a longer upper basically edge. You have a shorter lower edge. And the idea is you have some air. Air comes into this point, breaks up into two paths, right? And they meet. And they meet at the trailing edge. Okay, so air comes in. The normal theory you hear about what airplanes fly or how lift is generated is air separated into two streams. They have to eventually meet. So the top one goes through a longer path. The bottom one goes through a shorter path. So there's a speed difference. Right? So there's some law of continuity. So it says that, well, the air molecules have to meet. So air has to trailing edge. Okay, so if they have to meet, then there's a higher speed for W1, right? Or W1 is high because it has to travel over a longer distance. has traveled over a longer distance and meet with the bottom one, then the air on top has to move at a faster speed than the air on bottom. Okay. So you get something called the Bernoulli's principle, right? Bernoulli's principle says that the speed increase implies a pressure decrease. Okay, so this is a example of ideal gas law, PV equals nRT. So they have to go in different directions. So higher speed, you cannot have as much pressure because the amount of air is conserved. Okay, so the pressure has to decrease. So hence you have a pressure difference, right? So this says that pressure at the bottom is larger than pressure at the top. Okay. And then since pressure at the bottom is larger than pressure in the top, the pressure difference generates lift. Okay, so this pressure difference generates lift. And this lift would, either lift the airplane or turn the wind turbine. So that's sort of very straightforward, there's sort of very common analysis of how lift is generated. Okay. This is a common analysis. Okay, so unfortunately, it is not very correct. Okay, so Bernoulli's principle is there, has very little to do with how lift is generated. It has very little to do with how airplanes fly. Okay, so Bernoulli's principle is okay. The Bernoulli's principle is correct. There's nothing wrong with this principle. It's just that this is not how lift is generated. It's just not how lifts are generated. So there are some easy examples to actually show this Bernoulli's principle is not why planes fly. Can you think of some examples? So this theory of why lift is generated by pressure difference is really not correct. Really not correct. Can you think of some reasons why? Like some examples will show that this theory has problems. I think of, right? So I'm not asking you to say why, right? So paper airplanes is one example. Right, so this is flat wings. Okay, there's no airfoil. Right? There's no airfoil. It's just flat. So there's no speed difference between the top and bottom. So by Bernoulli's principle, there'd be no lift, right? The pressure is exactly equal. But paper airplane flies flat. Right? It will glide for a at least short amount of time. Right? So there's a more dramatic example of why this is wrong. Think of an actual airplane. Can you fly an actual airplane inverted? So if you turn the plane around upside down, will the plane still fly? Right? The plane still flies. You may not be super comfortable in the airplane, but the airplane will fly far. Okay, airplane can fly inverted. Okay, so it's not very comfortable, it's not very efficient, it's not very fast, but they can fly for indefinitely long, right? They can fly for a long time, flying inverted. But then by Bernoulli's principle, this should be impossible. And this is impossible by Bernoulli's principle. Because if you turn the airfoil around, then by Bernoulli's principle, the pressure is downwards. So you cannot fly for any, or you cannot fly for any amount of time. Okay, so that's again, because airplanes can fly inverted, then Bernoulli's principle is not a major factor on why you fly, on how lift is generated. All right, so again, right, another sort of question is, why would air meet at the trailing edge? Right, these are molecules, right? These are air molecules. Why does it care that they meet with some other molecule at the trailing edge? Okay, so if you put this into actual chamber and you look at airflow, they don't meet. Two molecules will move apart. There's no they don't meet, and there's no reason for them to meet. Okay, so these are not the right reason, even though they're widely taught. So one interview question that people often ask is for you to explain how lymph is generated. Right? And when you say this, if you say Bernoulli's principle, you may not go so well in the interview. And the unfortunate thing is the reference book gives this theory. And so the wind energy book gives this theory. It's not the correct theory, but we can't change the book now. So that's one reason it's not used as a textbook. Okay, so we don't guarantee what studying the book is correct. And this is what something that the book doesn't do well. Okay, book doesn't do the theory of lymph generation well. So how is lymph generated? How is lymph generated? Lymph is generated at a very high level because Newton's third law. Now that's how lymph is generated. Right? The reason is, as early in the class, is why is there friction when air is close to ground? It's because air is a viscous fluid. Air tries to hug the shape of the airfoil. Air, because it's a fluid, it's actually quite viscous, tends to stick close to surfaces. It hugs the air, it hugs the shape of the airfoil. So if there's an angle, right? If you have the airfoil lifted at an angle, then air comes in. Then air will get bent downwards. Okay? Air gets bent downwards. Well, if air gets bent downwards by Newton's third law, something has to go up. Okay? Because the airfoil is there, air gets bent downwards, and the airfoil has to be bent up, has to go upwards. And this is where lift comes from. Okay? So the shape of the airfoil is so you design the shape of the airfoil very carefully because you want the air to hug this as close as possible. So the better the air hugs this airfoil shape, the more it gets bent downwards. And you have this shape that's curving downwards, will get bent downwards. So for a given angle, the larger the force you have bending the air downwards, then by Newton's third law, the force pushes the airfoil upwards. Okay, this is why we still need that shape. The shape is important to get efficiency. But as long, if you have an angle and air hits this angle and goes downwards, you can get some lift. Okay, so this Newton's third law is really what sort of drives the airfoil upwards. Okay, so this Newton's third law is air is viscous fluid, airfoil bends it down, then air pushes the airfoil up. Okay, so the faster the moving speed of air, the more it gets bent down, so the more force there is on the airfoil going up. Okay, so this is third law, Newton's third law, and this is what generates lift. Okay, this really sort of generates lift for us. Okay. Any questions about this? Okay, so this is the design of airfoil. So the actual equations is quite complicated. It has to do with viscosity of air, has to do with temperatures, has to do with the exact shape of the wings, has to do with the angle you're hitting the air at. As all these are complicated, right? But at the end of the day, sort of the underlying principle is a fairly simple one. The equations will be very complicated once we start looking at this. All right, so of course there's a lift and a drag, right? So once you move the airfoil, if air is hitting you, then some of the force maybe go up, some of the force pushes you backwards. Okay, so there's a lift, there's a drag force, okay? And we try to sort of sometimes maximize the lift, right? The goal is often try to maximize the lift. Okay. Right? So there's more details you can see. Then this comes from NASA actually. So NASA is not very happy with the story that so most people know about how lymph is generated. So there's a lot of fancy pictures, simulations, actual experiments, in all these websites you can see. You can see sort of Newton's law in action. Okay. All right, so yeah, so the key thing for this is just to remember that it's not about Bernoulli's principle. It's not about Bernoulli's principle. It's sort of about a number of things. Okay, the speed is coming in, the angle of your blade, the angle of the airfoil, and the shape of the airfoil. And all these things come together to decide how much lift we can generate. And that's why sort of designing this is sort of very complex problem. Okay, that a lot of people are still working on. All right. Okay. All right. So more equations is we want to talk about the sort of the aerodynamic force, right? So once lift is generated, we want to understand how much force is in this lift force, right? How big is the lift force? Okay. So this lift force is what we want to look at is, so we won't have equation to compute the lift force because the actual equations computing the lift force is very complicated. Okay, so the actual equations is very complicated. We won't come near to where these are. So what our goal is trying to understand, what are the factors that impact lift? Okay, what are the factors that impact lift? If we can understand sort of the main factors that impact lift, we can at least know what to control. And how exactly the equations work out, maybe we don't know, maybe we take data and fit equations. But for us, from one engineering point of view, we need to understand the factor. Okay, what changes? How does lift change? Okay. Right. So if you fly an airplane, you can change how fast you're going and change sort of the angle of attack of the airplane. For wind power design, we are not going to change W, right? So this is the wind speed is given by nature. Okay, we're not going to change the speed of the air that's coming in. So unlike an airplane, where you can decide how fast you go, we cannot. Right? But we don't have this luxury. We're not moving. Right? So the main factor that we can control that matters is something called the angle of attack. Okay, so this is the main control variable we have to change the amount of lift force on the airfoil. Okay. Right? So angle of attack is just the angle that the wind is hitting your airfoil at. Okay, it can hit it, right? So there's two examples. Angle of attack can hit it straight on. Right? Angle of attack can hit it straight on at the nose of the airfoil, at the leading edge, or can hit at the angle, And by different angles, you have different amount of lift that's being generated. Okay, so you have airfoil, right? Wind is coming this way, so you can sort of turn your blade this way, and that will change the angle of attack. It will change the angle of attack of the wind coming to the airfoil. Okay. Right. Any questions about this idea of changing angle of attack? And so this is the main control factor we have. Okay, so change the amount of power we can extract, change the amount of force we can extract. The main control variable we have is this sort of angle of attack. Okay, this is the angle of attack, right? So the way the angle of attack works is, well, by changing your angle of attack, you change the total amount of force you have. Right? You change the total amount of aerodynamic force you have. Okay, and this aerodynamic force has two components. Right? So you have aerodynamic force that's sort of being generated on the airfoil. Right? One hits the airfoil, you have this force being generated. So this force is a vector force. There's two parts to it. One, this is straight up, this is lift. Part of it, this is drag. Okay, so this is, it's a force, it's a vector, it has two components to it. Right. So for us, what we care about in wind is we care about the lift force, because our blade is fixed on the turbine. Right, so the drag really doesn't do anything. The drag is just a force that pushing against the sort of the tower you're fixing. So what we want is we want to maximize the lift. Okay, so our goal is to maximize the lift. So this is the thing that generates electric power at the end of the day. Okay, the drag force doesn't do anything. We don't care about the drag force. Okay, so our goal is to maximize the lift. We want to maximize the lift. Right, and the way we do this is by changing the angle of attack. Because if you have an angle of attack, let's say at 0 degrees, then it may be that all the forces, most of the force is in the lift, but you may have a relatively small lift force. Okay? So all the force goes into the lift, but the total amount of force is small. If you hit this at an angle, you may have a much larger force. Okay, so some of this is wasted in drag, but still the component that's left over is a larger lift force. Okay, so the interplay is you want a larger overall aerodynamic force. You want a large fraction of this force to be lift. Right? So the point you try to hit is sort of, you know, the fraction of force that's lift multiplied by the total force. You want to maximize this number. Okay, so it's not always about maximizing the amount of force that's lift or the total aerodynamic force. We're maximizing the product of the fraction force that's lift and the total force you have on the airfoil. Okay, so that's why you change the angle. Okay, so this is what we're trying to do. We control the blade. We're trying to vary this to pick out the maximum lift. Okay, so when you design airplane, you care about drag. We don't really care about drag. Drag doesn't enter into our calculations. But we only care about the sort of the part of the force that's lift. All right, so there's a bunch of equations that goes into this now. For us, really, what matters is this equation. Okay. There's a lot of parameters. Don't worry. So what this equation says is, well, so how much force do you have? Well, the force depends on the square of the speed. Okay, so let's parse this one by one. Depends on the square of the speed. Right? Depends on the square of one speed. Depends on how large the area is. Right? So you want one turbine, well, how much area are you hitting on the blade itself? Depend on the air density and depend on this coefficient of lift. Okay, also depend on this coefficient of lift. This coefficient of lift is a function of alpha. Okay, so as you change alpha, there's sort of different amount of stuff you can extract from it. Okay? A different amount of lift you can extract from the total force. Okay, so our goal is basically to maximize this number, this lift force. So coefficient just means the amount of force that's lift divided by the total force. That's the lift coefficient. The drag coefficient is similarly the amount of drag divided by the force that's drag divided by the total force. Okay. All right. Okay, so again, we won't have equations to compute this. I won't give you the equations, but for now, the important thing is to understand the dependence. Okay, when we're changing the angle of attack, we're changing the CL, right? This coefficient of lift. Okay, so it's not a constant multiplying, it's just some function of coefficient of attack. Okay, so this is a round theory. Okay, so this again, if you repeat the Bernoulli's principle, we try very hard to explain why the angle of attack matters and how, you know, the changing speed and changing length. All this is in some sense bogus, right? This is bogus theory. Okay, so we're now going to explain things through different distance air molecule travels. What we're going to say is angle of attack changes, the way airflow changes, more air may get bent downwards, so you have more lift. Right, so what we care about is this, right? How much lift you guys generated. So it depends on the angle of attack, right? So some angles, you have a lot of lift. You can, if you bend downwards enough, you may have negative lift. Right? You could have negative lift force, okay? So, or you can have a place where there is no lift force. Okay, of more interest to us is actually this case. Okay? You increase the angle of attack so much that nothing is being generated upwards. You have no lift, where everything becomes drag. The entire force becomes drag. Okay? This is actually a useful thing for us to know, to consider. So can you think of a situation where it'll be an event where you want to actually operate wind turbines when there's no lift and everything is drag? So when do you want to operate a wind turbine? When there's no lift. So all wind turbines have this option. So you look at the control mechanism inside the turbine. There is a way to control the turbine such that the airspeed is locked. Okay, so Ishan says in chat, right? Many people says high wind speed, so too fast to operate safely. So that's the right intuition. But why would it be too fast to operate safely? Like, why is operating very fast not safe? What is unsafe about operating at a very high wind speed? Like, what exactly goes wrong? Right? So the mental image you should have, if you don't lock the blade, if you don't, if you still operate the blade at very high speed, the thing actually blows up. That's the correct mental image you have. The thing blow up. But what exactly make it blow up? Right? Yeah. So the last answer is correct. It generates too much power. So think about it. When you turn the blade, there's force. The lift force eventually becomes power. And the power has to go somewhere. Okay, the power has to go somewhere. And where the power goes, the power has to go to the grid. But inside the grid, the power has to be consumed by some load. So it's actually not uncommon for wind turbines to be in a situation where they're generating too much power for the grid. Okay, so the grid may say, I don't want your power because I can't dump your power somewhere. Okay, the grid doesn't want your power. But then if you're still operating at very high speed and the grid can't take all the power you're generating, well, power has to go somewhere, right? Energy has to go somewhere. And then what happens? The whole thing blows up. So if you're interested, you haven't seen this, go to YouTube and Google wind turbine failures. It's quite impressive. It's quite impressive the things you'll see. And they blow up, they fly around, they do all those kind of things. So being operated at a regime where there's no lift is actually quite important. Okay, so if you go, yeah, go ahead. A question?
Yeah, so you said that drag isn't important, but I imagine at super high wind speeds, at some point you would have really high forces from the fact that you're the wind's just pushing against these. Is there like any design things that you can do for that?
Yeah, so we designed the tower to be mechanically set, right? So the tower design, you have to be able to be stand up to this kind of force. So if you go to all this big field, actually, so every wind turbine we use has to be tested in practice. So when they test your wind turbines in the field in practice, they really don't test how much power you can generate, how efficient you are in generating power. That's sort of not their problem. What they test is, can you stand up to high wind speed? Can you lock your blade? So locking blade means you're generating no lift, it's all drag. Can you lock your blade? And can your tower stand up to this kind of force? So that's where they physically test all those things. And I've been to a site. So I've been to this site that tests this kind of things. And they have very high wind. They look at the blade to say, okay, we get to the speed. Now we want to lock the blade. Can we lock? So I've been to this kind of site. But then I was a little bit scared there, right? Because if it fails and it's not successful, I don't want to be hit by a blade, right? But the sort of the people who run this kind of test, you have engineers whose whole job is to do this, right? So it's important to be able to lock the blade to stand up to the force. Okay, so this is an important operation, right? So to have, just to keep in mind, right? So we have angle of attacks. Sometimes you angle attacks of 90 degrees. That may not make any sense to you, but this is where we want no lift force. It's important to be able to stop the blade. And a lot of wind turbines failed. The first generation wind turbine failed. That's because they couldn't really do this. And then you have blades flying off turbines. That caused a lot of. So if you go back to the 80s and you read some of the news report, they'll say wind power will never work because the turbine blew up. But nowadays we're much better at doing this now. It's very rare to nowadays see a turbine fail in this way. But still, this are things you'll see. If there was ever adequate load, is rotational speed ever a concern? Yes. So load is a relatively constant. Okay. The load at the grid always balances generation versus load. There is never excess load in the grid that's not being served. Because the grid always balances. So what you care about is if the wind speed suddenly picks up to be very high. There is not much load I can dump the power from the wind turbine to. The load is being served by something else. So dump the power from the wind turbine to a load, something else has generated less load. Okay, so that's actually a very hard problem to solve. So that's one challenge to operate a wind turbine. As things move very slowly, you're not going to ask a nuclear generator to back off generation to accommodate wind. Even gas are not fast enough. Gas are not fast enough, right? So as we go along the course, you'll see the way we deal with this is actually we put a big resistor close to the turbine. And so if you really have to burn power, go through that resistor. Okay, you may melt something, but at least you don't have a failure, catastrophic failure. But nowadays, people are replacing that with storage. Right, so power goes somewhere. Yeah. The last question on this topic. Go ahead.
I have one more question. So, is there an angle of attack that's low that could reduce the lift force? That could make both forces close to zero, or is that unstable?
That's unstable. The force has to go somewhere. Right? There's that much force on the blade. So you have something in the wind hits it. Well, there's a force. Right? You can make so to make lift zero is normally some drag. You cannot make both zero. You're a piece of metal in wind. There's some force on it. Even if you operate very inefficiently, there'll be some force. Okay. All right. Okay. Good. So there's something to keep in mind. That's the angle of attack. It's a very important parameter. Okay. So what you have in practice, you often have a plot like this. I have an angle of attack. And by changing this angle of attack, I can change the amount of lift I have, right? So there is some angle of attack, whereas the lift is zero. There's no positive lift. But from this angle of attack to some very large number, I get some lift. Okay. As I vary this angle of attack, I change the amount of lift I can generate. All right. So this curve, this is normally an empiric curve. This is sort of a curve faded from data. So we really, there are equations computers. We're not going to go to any first principle equation computing this. From data. But you can imagine I have a blade that sort of varies the angle of attack. I record the amount of lift I have this kind of curve. Okay? And the thing to remember is you sort of, right? So there's a maximum lift. And there's alpha max. There's a maximum lift. You sort of want to stay away from this maximum lift. You want to stay away from this maximum lift. So the operating regime is actually away from the maximum lift in this regime. Okay, you want to operate in this regime, right? Because the maximum lift is really not a stable operating point. Because you don't want the airfoil to stop. You don't want a lot of turbulence on your airfoil. So if your lift gets larger and larger, what happens? So your angle of attack is too big. It is true that you have a very large force, but then you tend to have a lot of turbulence here. And you want to operate in this region where you don't have a lot of turbulence. Turbulence creates a lot of mechanical stress on the blade. It makes the, and you have 3 blades, so make the operation of other blades very complicated. So we normally stay away from the maximum lift a little bit. Right? We operate in some region of operation. Okay, any questions about the curve? Right, so often if you buy a turbine, they say, okay, this is your curve. Right, they give you this curve. And they tell you, oh, this is operating region where your turbine should operate. Okay, so that's normally a curve that's given to you. Okay, so let's do some calculation. So this is a typical example we have. Okay, so we have a 3-blade wind turbine operating at a given angle of attack. Okay, so we have some angle of attack. Where at that angle of attack, we get a aerodynamic force. So the total force on the blade is 2000 newtons. And at this angle of attack, the lift coefficient is 0.95. Okay, so a lot of the power is actually being extracted. There's a lot of the force is actually going to the lift. So the center of gravity of each blade is 30 meters from the hub. Right? So the length of the blade, you can think of 30 meters from the hub. We want to generate the torque being generated by 3 blades. And then if the blades rotate at 30 RPM, we want to compute the mechanical power. Okay, so this here, we're now going to start to see how does the force go into power. Right? So the force has the blade that generates the lift force. Lift force gives you a torque because you're turning this. Right? You have a torque, you're turning the blade. Once you turn the blade, then there's a mechanical power. Right? Turning torque is power. Okay, so this is how we get to power, right? And this is a useful review of a bunch of equations. I'm guessing you should all seen before, but you probably all forgot. Equations converting torque to power, right? Force to torque, all those kind of things. Okay, so it's a good review of this kind of equations we use in the class. Okay. Right, so let's look at the solution. Okay, so what do we have? Well, remember we have an airfoil, right? So this is the hub. So the hub, you can think of, you have airfoil, right? So this is the hub. This is the hub here. So your length of the blade, right? So we have some blade. And the center of gravity is, so the center of gravity, so you have a hub. This is your center of gravity. This is 30 meters. And I have some force. I have some force here. Right? I have some force on the blade. The blade is 30 meters away from the hub. Okay. Right, so the total force is 2000 newtons. The lift force is a lift coefficient multiplied by the total force we have. So the problem gives us lift coefficient 0.95. So yeah, 0.95 here. Oops. What did I do? Okay, I have no idea. Okay, there we go. So the force is 0.95. The coefficient is 0.95. So this is 0.95 multiplied by 2000. And the total lift force is 1900 newtons on it, right? So now we have a blade that's turning, right? You have this turning force, that's 1900 newtons. So when we talk about the blade, we don't normally talk about to the tip of the blade, we talk to the center of gravity. Right? So like in physics, we have an object. When you think about force on the object, you think about the force on the center of gravity of the object, right? Not to the tip of the object. Okay, you have center of gravity, center of mass. Okay, so if the lift force is 1900 newtons, and the center of gravity is 30 meters away from the hub where you're turning from your reference, But how do we compute the torque? Now remember, how do I convert a linear force that's turning you to a torque, to a rotational torque?
Force times distance.
Force times distance, right? So this is, simple equation, that's something to remind yourself. So I have a torque on one blade, right? So this is torque is how much linear force I have at the center of gravity, multiplied by how far away I am, right? Multiplied by distance. So this is 1900 multiplied by 30 meters. So this gives us, right? So this gives us a torque on one blade. We have three blades. So the total torque is 3 times the torque on a single blade. Distance (171 kilonewton meters). Right, so this is our torque. This entire torque generated by three blades that's turning around. Okay, so F times R. And how about the power? What about power? How do you relate torque to power? So this is the power that eventually gets converted once you go through a generator to electric to current, right? So how much mechanical power now is being exerted as a blade extracting?
The torque times frequency.
Torque times frequency. Specifically, what frequency?
Angular.
Angular frequency, right? So the important thing to remember is angular frequency times torque. So often the common mistake is that people will see, oh, 30 RPM and think of that as a frequency. You really need to talk about the angular frequency, right? So this is the angular frequency. So I'm going to write down the angular frequency times torque. Right, so the total torque, angular frequency. So the angular frequency, this thing is in radians per second. So we need to convert our frequency, which is most times in RPM, to something that's radians per second. So it's very natural to talk about one turbine frequency, one blade frequency in RPM. They typically rotate at 30 RPM, things like this, right? Or 50 RPM. But in calculations, we need this to be in radians per second. So let's do the conversion. The conversion is 2 pi times the frequency in RPM divided by 60, right? Times the total torque. Okay, you divide by 60 to get rotations per second, multiply by 2 pi to get radians per second. Right, so this is 2 pi times 30 over 60 times the total torque, 171 kilonewton meters. And we get something like 5.2 kilowatt. Okay. Questions about this? Okay, so a common mistake for this type of problems, you'll see a problem like this in your homework and in exam. These are very common type problem. As one sort of, you forgot to convert the frequency to angular frequency, right? So you either forgot to multiply by 2 pi, a very common mistake, or you forgot to divide by 60, right? So it's rotation per minute, you forgot to convert to rotation per second. So this is a common error. Right, so another thing is there are 3 blades, right? There are 3 blades, so you need to multiply by 3. Right, so 2 common errors: people forgot to multiply by 3, or get the frequency conversion wrong. It's just something to keep in mind, okay, for this kind of problems. Okay, so most problems in this course are not tricky. There are some equations you can plug in to get your answer. Just plug all the right things into the equation. Okay, this is. Any other questions before I answer the question in chat? Okay, so Isha, that's a very good question, right? So this problem says 3 blades, and the torque and the power all gets multiplied by 3, right? So it's like more blade, more power. So why 3 blades? Why do all wind turbine, virtually all wind turbine, have 3 blades? Why not 4? Why not 8? That's like build more blades.
Doesn't the increased number of blades lead to more turbulence on the path?
Right. So one big factor is turbulence. Because once a blade sweeps through the air, there's actually some turbulence in the air. So if the next blade comes too close to it, because there's turbulence, you actually don't get that much power when you sweep through. Okay? So when you have multiple blades, when you sweep through, you don't get that much power. So turbulence is a big factor. Okay? So it's not, so it doesn't scale linearly anymore. So it scales linearly to 3. But then if you go any more, it doesn't scale linearly. You have a diminishing return if you go to say 4 or 5. Another reason is the mechanical stress. These blades are really big. The tower is really tall. You have to withstand a lot of force. If you build more blades, it's become too heavy. And you cannot build blades as large because mechanical stress. Okay, so 3 is sort of the right trade-off. And also that's a reason why you cannot turn very fast. But y'all look at this, seems, oh, the RPMs or this thing scales the RPM. So why don't we just turn it faster? If you turn it too fast, you also get into turbulence issues. So it's turbulence and mechanical stress. But another thing to think of is why not 2 blades? Right? If it's too heavy, 3 blades is also heavy. Is it worthwhile to build 2 blades, maybe a bit larger? Right? You know, power is area times, right? So there's area matters. How much power can extract? Area matters. Right? The sort of the distance, right? The center of gravity matters. The distance from the hub center of gravity matters. So I build a blade to be larger. Maybe I get more force and longer center of gravity. So maybe that will, be more beneficial. So why not 2 blades? It's very, very, very rare. You see 2 blade wind turbines, large wind turbines. Is it worthwhile to build a huge 2 blades? Just build them really big, really long blades. Build 2 of them. Any ideas? Right. So 3 blades also have a benefit that the weight is fairly evenly distributed across the system. As you have 3 blades turning, at any point, the weight is actually evenly distributed. This is like the 3-phase power in AC power flow. But 3 of them, the weight is even distributed. We have 2 blades. What happens is, depending on the orientation of the blades, the weight distribution is very different. For example, they can be straight up and down, or they can be flat. And it creates very different weight profiles on the tower and the blade. So if you build a 2-bladed turbine, what happens is the turbine wobbles back and forth. Because it's vertical is one weight distribution, it's horizontal is another weight distribution. So you see this kind of wobbling. And if you build a blade very big, this wobbling becomes very, very so the mechanical stress from this also becomes too much. Okay, so 3 is sort of good trade-off. 3 is good trade-off there. Give you mechanical balance. It's the weight for different configuration is actually all evenly distributed. Right, so the exact same calculation for 3-phase power will tell you this. The sinusoidal shape, you add a sinusoid, they all cancel. Right, so the weight is very even distributed. So 3 is nice, better than 2. 3 sort of give you, good number of blades and reduces the turbulence. Okay, so it's a good trade-off. Good trade-off. Right, so it seems like this design will be fairly robust. 3-blade turbines. Any other questions for this? Okay, so this is the sort of the basic calculation you'll see. And then you see something called, so the angle of attack, this just reinforces that the angle of attack cannot be too large. you really want to avoid this stalling. Okay, this stall creates all kind of problems. Mechanically, this creates a lot of stress, creates turbulence, creates everything. They want to avoid from the angle of attack being too large. Right? That's why you don't operate close to maximum lift. You want to back off against the maximum lift a little bit for this kind of stability reasons. Okay. All right, okay, so we'll stop here today for the class. Next class we'll pick up from a point is because angle attack is a nice number. The trouble with angle attack is angle attack has to be referenced to the wind direction. You really imagine the angle attack reference to wind, not to ground. Okay, but then the wind direction changes. Wind is a vector again. So the angle attack is something sometimes hard to measure because we don't sometimes know the true direction that wind is coming in. Okay, so next class we'll convert the angle of attack to something called a pitch, which is just an easier angle to measure for us. Okay, so we'll convert angle attack to a pitch angle. And now, so pitch angle control then becomes the main control mechanism for wind turbine power. Okay, all right, so we'll continue from here next class. And hopefully I'll see you guys in person next Wednesday.
Thank you.
Thank you.